Recordings rolling. It is Wednesday, February 18th. Okay, so you guys, honors, I'm doing technical puzzles with you guys. So I'm going to do the technical game, just a bunch of questions. Now, a lot of these are related to, of course, what we've been studying for about the last week and a half, these fluids, right? There are a couple of questions that are, outside the topics a little bit. So if we have time, maybe we'll hit those too. That'll be a little bit extra. But the quiz coming up on Friday is just going to be on the fluids that we studied so far. So I think about this gas chamber. We might do this in class. We have a little extra time, but this gas chamber is not going to show up on the quiz on Friday. Right. Same thing with on the back. There's it's like a bridge that expands due to temperature change. Right. We haven't really covered that. Might do it today, but I won't be able to quiz it. Right? If you haven't got your harmonic motion waves quiz yet, then those have been back. So of course you guys can do quiz corrections if you like. Right. Right. So. Here, before we hit this page, let's do a little bit of review with the guys. Let's do some review. Main ideas and equations here. You have to have density is bound creating volume. Guys, what's the density of water?
1,000 kilograms per.
There you go. There's 1,000 kilograms in a cubic meter of water. Right? Right. And then, what about, what about this object? Do you guys think this object has a density greater than or less than that of water? Yeah, greater than. If I threw this in water, it would sink to the bottom, wouldn't it? Okay, so if I threw this into the Pacific Ocean, will it sink all the way down to the bottom of the ocean? Yeah, go all the way to the bottom. Okay. So as it goes down, 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 the pressure is getting greater, greater, greater. But it turns out the net force on it, this buoyant force, is actually the same all the way down. Okay. That brings us to this point. And so pressure, I'm talking about gauge pressure here. It's just rho gh, density of the surrounding fluid like water, and its gravity times h is the depth, how deep you go, right? Now, if you want absolute pressure, you could also add the atmosphere as pushing down on top of that and say pressure atmosphere plus this rho gh. That would be the absolute pressure, right? The resulting buoyant force, this is a force over here, very similar looking formula, but it says, but you really don't care how deep it is. What you do care about is the volume displaced, right? So if this is halfway down the ocean or all the way down the ocean floor, the buoyant force is the same, because all these variables would be the same. Yeah, totally. Actually, I just showed you guys this Archimedes principle. So the value of the buoyant force, the magnitude, turns out equal to the weight of usually water displaced or fluid displaced in general. Right? And you can further break that down to density of the fluid times volume displaced, and then times gravity field. Right? I think, this is okay. This question is going to come up later today. There's going to be like an iceberg floating in the ocean. Okay? And I'll tell you the density of the ice and the density of the water. The question is going to be like what percentage of the iceberg is, well, depending on how the question is framed, either above or below the water line, right? So we'll be able to make use of this later. We do the up one. Okay? Yeah, and maybe on the quiz on Friday, I might change the scenario to a wood block, and the wood block could have some unique density, right? That's maybe not ice, right? I bet different kinds of wood have different densities. Right? We got Pascal's principle, which is that the pressure in this fluid is this contiguous fluid is the same everywhere. Right? So the same pressure here as it is here, same pressure, same pressure. Okay? And then you can use that to create this hydraulic lift. You can get a mechanical advantage. Pressure is force per unit area. So different cross-sectional areas, you got different forces. These YouTubes are fun. I have to put one of these on the quiz. So if we get some spare time later today, maybe I'll throw you guys a YouTube, pick up something. Okay? What if you have a dense liquid down here? Maybe this could be water. Maybe these other three are different kinds of oil. Okay? The idea is that the pressure here is equal to the pressure here. I mean, that would be Pascal's principle anyway. Pressure here. And so then we can craft a story and say, okay, well, what led to that pressure? And so they've each got the atmosphere pushing above, the left and the right. And so here's the pressure on the left, here's the pressure on the right. They each got the atmosphere. Right? And then each have these rho GHs, rho GH, rho GH, rho GH. Right? So I add up all the rho GHs. Right? And then that gives you equal pressure left and right here. And some of this cancels out, like the pressure atmosphere cancels out, this rho GH not. It's the same liquid, same height. And so that cancels out. Right? And you're left with whatever there. Okay. You could, there are different versions of these. There's a version where you cap one end, so the pressure from the atmosphere does not cancel out. Right? So that could be a variation. Right? Let's get this water flowing. Right? So there's this conservation of flow. The flow rate is the same everywhere in the system. Okay, and you can play around with this equation a bit and rearrange it so you get cross-sectional area times the linear speed of the usually water. Okay? And that product is conserved throughout. So let's think over. So A1B1 equals to E2. Okay. Now, okay, so careful. If you get a pipe question like this, it's really common to be given not the cross-sectional area of the pipe, but the diameter of the pipe, or sometimes even the radius. Okay? Yes. Suppose, let's see if you remember this. Just kind of eyeballing this picture, it looks like the diameter ratio is 2 to 1. Does that look like pretty close to a 2 to 1 ratio in terms of diameter? And if that's true, what's the ratio of the cross-sectional areas? Be 4 to 1. Yeah, right. Because this would have 4 times the area that this has. Because now we have to think in 2 dimensions. Ooh, diameter is 1 dimension. Area is 2 dimensions. Is that true? So you take that factor and square it. So 2 squared could be 4. Right? Now, to go one more step, if there's some water flowing through here, its own speed. Right? Is where's the water flowing faster? The fat pipe or the skinny pipe? Skinny pipe, it's a faster linear speed. In this particular case, how many times faster? 4 times. Yeah, 4 times. Okay, because this area 2 is 1/4 of area 1, so it have to be 4 times as fast to compensate. Right? Wouldn't that be? Okay, hey guys, here. What if? Here, I'll throw some numbers up here. What if? I'm just playing out this formula. What if the original area is like 8 units? This is going at 10 meters per second. Okay. And then over here, I got 1/4 of the area. So that's down to 2 units. Now, this is equal. So what is V2? 40. Yeah. Guys, what's 8 times 10? 80. What's 2 times 40? Also 80. Ah, do you guys see this conservation principle? Is that's right? Of course, I could throw some units like square meters and meters per second. Okay, but okay, so we got conservation of flow, conservation of flow. Okay. Okay, finally, the last one you care about for your quiz coming up in a couple of days is what's going on with the pressure inside this fluid, right? And that's answered by Bernoulli principle. Right, so we derived this about a week back from conservation of energy. You said the conservation of energy, like potential energy, kinetic energy, some other kind of energy, okay? And divide every term by volume. You get the expression in terms of pressure units, like pascals. Okay, so now we got some internal pressure on the fish here. This fish feels some pressure pushing on him. Okay, and we got a rho gh term, 1/2 rho v squared. Right? So something about the water flowing. Okay, and then when he swims to the skinny pipe, right? Well, there's a height change, so these brown terms are different. There's a speed change because cross-sectional area is different, so these green terms are different. Okay, so he feels a different pressure on him. Okay, so we'll solve some of those too. All right. Oh, yeah, I almost forgot about this one. Right, this is a good one to know. This can pop up. Okay. What if you have a tank of water and maybe a hose running down? You want to know what's the speed of the water flowing out. Okay. So you can also solve this with Bernoulli principle right here. Let's walk this. So is the atmosphere pushing down here approximately the same as it's pushing in on this hose right here? About the same pressure? Okay. So this pressure from the atmosphere cancels out. Okay. And then what's the height of the water at the nozzle of the hose? 0. So this goes away. Pretty. Okay. Now, if it's a really, really big tank of water and a really skinny hose, what's approximately the speed of this water level moving down? Yeah, very, 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 very tiny, negligible, very close to 0. So I'll just get rid of that term. Okay. And it boils down to just this rho GH all manifests as 1/2 rho v squared at the bottom. Okay. Okay. The density of the water cancels, and you get this flow speed is square root 2gh, exactly the same as it was when Galileo was dropping items off the tower and they were crashing into the ground. It was the same crash speed, wasn't it? Same thing. Thanks. All right. Yeah. Right. That's the main run down there. All right. Let's look at this page. This page. All right. So I have lots of different versions. I'll probably swap through different versions here. So. Okay. All right. Now, I want to skip the first two and maybe come back to those later if we have more time in class later. But let's definitely go to ones we've been doing in class. All right. You know what? Actually, let's start with that because I think some of the ones in the back are a little bit easier than the ones in front. There's some challenging questions on the front. Okay. So same thing. These top two. Let's skip those and come back to those. Let's start with number 8. Number 8 right here. Oh, sorry, 108. Okay, say number 108. Right, so hey, look, that looks like a hydraulic lift. Same as that. That's the first version there. Okay, so I'm gonna redraw this here. Okay. Now, if you're lucky, maybe you have the same numbers I do, then I'll pick a different version later. Okay, so we got a hydraulic lift, looks like this. Got a piston here, piston here. This is some hydraulic fluid. Okay. And I told you there's a car with a weight of 12,000 newtons. So here's a car. I'll say mg for the weight is 12,000, and that's newtons. Okay. The diameter of the large piston is 4 meters on my paper. So I'll say diameter equals 4.0 meters. And the diameter of the small piston is diameter equals 0.20 meters. That. Okay. So the question is, what is the input force on the side? I'll say F, effort force. Right. So some input force here is going to push on this fluid, which pushes up on this large piston, which is going to raise the car. Right? You see that? And the guiding principle here is Pascal's principle. The pressure, which is force per unit area, is the same on both sides. So we got area 1, area 2, force 2. That gets it far? Yeah. Of course, our ultimate goal is to find this force, which is the input force. So that's the goal. Okay. You guys, notice I did not give you the cross-sectional areas, but it did give you the diameters, which is different. What is the area of a circle based on its diameter? Yeah, pi over 4 d squared.
Yeah.
Okay. So we're solving for this force. Okay. I'm gonna go pi over 4 times diameter squared. And here, I'll just go and plug in diameter. So this is 0.2 meters. And don't forget though, that's definitely being squared. It's really, really important that you square this. It's brought from a linear concept to an area concept. 1 dimension to 2 dimensions. Okay. Over here, what do I plug in for this F2? How about the weight of the car? Okay, that's the force direct push against. 12,000 newtons on my paper, and then your paper is probably different. Okay. And then this cross-sectional area is like pi over 4 times, okay, and then my second diameter is 4 meters, and that's being squared. Gotta square that diameter. You see that? All right, now guys, if you want to simplify this a little bit, what could I cancel out on both sides?
Pi over 4.
Yeah, it's pi over 4 bit. Green. Okay. So it's really, really important that you do square the diameters. But if you somehow forgot the pi over 4 bit, which just turns it into a circle, that would not matter to the answer anyway. Okay. So, we're getting close here. So force equals, not the algebra step after you. I just have to take this small square diameter and cross multiply it. So let's take 12,000 newtons times 0.2 meters being squared over 4 meters being squared. That force equals, okay. And let's see what I'm getting here. Okay, so I'm getting 30 newtons on my paper. Is that an answer choice? Yes, that's an answer choice on my paper. Okay. So are you guys also getting an answer choice on your paper? So working out?
Yeah.
Yeah. Okay. So just to go from what I gave you to the very last step, so you can do a shortcut and check. If you very simply take the weight of the car and multiply by the small diameter squared divided by the large diameter squared, that should give you the answer. Okay. Guys, working out. All right. Let's go next one here. Right, so I got this pipe with probably water flowing through it. This is, yeah, okay, yeah, it says water, which, okay, we know what the density of water is. Because on the quiz, I would print the density of water, so I wouldn't expect you to memorize it. You know, okay. And I gave you guys these cross-sectional areas, area 1, area 2. Okay, no, so this time I actually did give you the areas. But if I gave you diameters, you know how to get the areas because we just did that last one. Okay. And I gave you one of the speeds. Actually, let me pick a different paper here. All right, these two go hand in hand. So first question is a conservation of flow question to figure out what's the speed of the water in the skinny pipe. And then the follow-up question is going to be, well, what's the pressure inside? So if you sent a fish swimming through the system, what would the pressure feel like? And so one at a time here. That's going off my paper. This cross-sectional area 1 on my paper says 4.0 square meters. And this cross-sectional area 2, the skinny pipe, says 1.80 square meters. I have an initial speed, call it V1 of 15 meters per second. Okay. I know it's going to be going faster through the skinny part of the pipe. I'll call it V2, and that's the first thing we got to solve for. Okay. So let's do conservation of flow. A1 V1 equals A2 V2. Okay. Now this area 1 is 4, that's square meters. And the V1 is 15 meters per second, or whatever it is on your paper. My numbers are probably different. Okay. This area 2, it's getting part of the pipe, this many square meters, and then I can solve for V2. Okay. Very simply divide over the other area. So V2 equals, here, spell it up. 415 divided by 0.8 meters per second. Okay. All right, make sure that's a choice on my paper. Yes, yes it is. So that's showing up as an answer choice. Okay, how about you guys? Is that working out for you guys too? Yep, it's working out. That's right, everybody's getting that. Okay. Okay, now hold on to this because there is a follow-up question, and that's what's the pressure inside the narrow part of the pipe. Now I know the pressure is going to be small in the narrow part of the pipe, or smaller than the large part, because the fluid speeds up. Okay, you guys ready for pressure? Okay. All right, let's move on here. Okay. So again, hold on to these notes. We might need some of these numbers. Okay. Let's set up Bernoulli's principle. Bernoulli principle, which says this: the internal pressure, and say part 1, plus density of water times gravity times height 1, plus 1/2 rho v squared equals pressure in a different part of the pipe plus the rho gh in that part of the pipe plus 1/2 rho v squared in that part of the pipe. So Bernoulli principle. Hey, you guys got that? Okay. Now this particular question, I don't know if I'm going to do this on the quiz necessarily, but do you guys see this pipe is all horizontal? Because the fact that it's all horizontal, there's no height change basically, right? Center of pipe, there's basically no height change. Okay. How can you simplify this particular equation?
And so,
Yeah, because this H1 and H2, they're the same thing for this particular question. So this and this don't actually contribute to any kind of pressure change because the height doesn't change. Okay. So what started out as 6 terms, I can really narrow down to just 4 terms. So the initial pressure plus 1/2 rho V1 squared equals the final pressure plus 1/2 rho V2 squared. Okay, so that's nicer to work with. Okay. Okay. Now, I told you in this box what the initial pressure in the large diameter pipe is. Now, my paper says 250,000 pascals. Here, side thought here. Let's do a side thought. Because what again is, how many pascals of pressure are you sitting in right now in this room? Approximately 101,000?
Yeah.
Okay, 101,000 pascals? Okay. So if you had the pressure in like my pipe pressure is 250,000 pascals, approximately how many atmospheres is that?
that's like,
Yeah, about 2.5, right? About 2.5 of those 100,000. Right? Pretty close. All right, so of course we're going to plug Pascal in here, not atmospheres, because we base this on units. So my number is 250,000. Okay, that's pascals. Okay. So the big part of the pipe, the density of water, you guys told me earlier, is 1,000 kilogram per cubic meter. Okay. Again, I'm not going to expect you to memorize that. I would print that number on the quiz if I wanted you to use it. Okay. And the initial speed. Right now, here's where you got to go back to the previous question, because took it too far. Remember, I gave you the initial speed right here. Guess from that. Okay. So for my paper, it says 15 meters per second. Okay, don't forget to square that. I'll square that. Okay. Okay. And then we want to know what's the pressure in the skinny part of the pipe. Okay, and then plus 1/2, got 1,000 kilogram per cubic meter here. Okay. And then speed 2, well, that was the answer to the previous question, which that's what we call conservation of flow for. Okay. So normally if you're solving a Bernoulli equation, you do have to solve conservation of flow first. And that's what we did before. So I got that. That's like, in my paper, it's like this many meters per second. Again, don't forget to square that. Got to square the speed. And plug that in. Okay. All right. So now we got all the parts lying around. We just got to push this in the calculator, do a little algebra rearrangement, subtract this over, get P2. So P2 equal. You know what? I'm going to throw in the middle step. Let me throw in. Here, I'll switch each color so it kind of stands out a little bit. So I'm giving you guys an extra step right here. 250,000 pascals plus, because I wonder what numbers these actually look like. 500 times 15 squared. This is like 112,500. Again, pascals. Okay, I want to know P2. Okay, and then okay, this is like 555,000 pascals right here. Okay. All right, now let's go ahead and get what is P2. It's P2 right here. Okay. So we got 250,000 plus 112,500. That's not great. Then I'm going to subtract over this bit right here. Okay, because the water is flowing so fast through this skinny part of the pipe, sort of think of it like it's consuming a lot of the pressure units. So I'm just going to subtract that over. I'm getting a big negative number. That's pascals. Guys, can pressure be negative in a fluid like water? Yeah. And what that means is, say like let's say outside this pipe the pressure is just 1 atmosphere. This pipe's just going on sidewalk or something. Okay. If the pressure inside the pipe initially was like 2.5 atmospheres, 2.5 atmospheres inside, 1 atmosphere outside, isn't there a pressure differential? It's like pushing on the walls of the pipe, trying to make it explode. Right, it's trying to do that. But when you get to the skinny part of the pipe, okay, and we still have 1 atmosphere outside, okay, that's not good. But inside, now I have a huge negative pressure. It's trying to vacuum the pipe. It's trying to make it implode. That's what it's trying to do. It's trying to stretch it down. Is it? Okay. Last detail here is if you want the exact multiple choice answer, I did change the unit. You see I changed the unit to kilopascals. Yes, kilo is a factor of a what? 1,000. So for my paper, it'd be this many kilopascals, kPa, kilopascal, thousands of pascals. Okay. And yeah, that's an answer choice. Okay. Is that working out for you guys too? Okay. All right, any questions on any of that? Okay. All right, let's narrow it down. Okay, so we did these here. Gonna flip back over to the front now because I told you guys some of the ones on the front are a little bit challenging. Okay, I think the next easiest one is actually this iceberg question. Okay, see number 90, this iceberg question. Let's go ahead and tackle that. So number 90. So yeah, I'm on the front, down at the bottom. The front bottom, down at number 90. Okay. Let's get an ocean level. Let's get an iceberg floating right here. Here's an iceberg. Okay. And I told you the density of salt water. So I'll say water, but it's really salt water. You guys think salt water is a little more dense than fresh water? Yeah, and that's what this is saying too. So we'll go ahead and use salt water here, kilogram per cubic meter. Okay. Okay, and the density of this ice, call it rho ice, is about, now my paper says 910 kilogram per cubic meter. I think I looked this up and then rounded it up or down a little bit for everybody's paper. Okay, maybe it's, like not pure ice, maybe it's dirty ice, maybe it has some air bubbles in it, right? So maybe everybody's iceberg is a little bit different, okay? Okay, and the question is, what percentage of the volume of the floating iceberg is submerged, right? So that could be this hashed in bit right here. What percentage is that compared to the entire iceberg? Okay. And so let's properly go through the whole process. Now, of course, I think you guys have the thumbnail notes for this, or you got the. Wait, do I have a wall poster for that? Did I not make the iceberg?
Yeah, buoyant said the worst one, but
Huh. Okay, well, that's okay. We'll go through this process because this is a good process to know, right? Okay. Okay. Now, you guys know at the end of the day, the answer is just going to be the ratio of the densities, but let's see what leads into that, right? Could you sort of rediscover that or prove that? So, guys, what force is pulling down on the ice?
that's good.
Yeah, mass of the ice times gravity field. Its own weight is trying to make it sink down to the bottom of the ocean. What force is holding it up? A buoyant force. And buoyant force breaks down into what times what times what? Density of the water. Yeah, displaced volume and gravity field. Right. Now I hashed in the displaced volume because that's not all the ice. Only some of it. Most of the ice is pushing water a little bit, but not all the ice. Okay, you guys got that? Okay. Now the guiding principle here is equilibrium. So I know the sum of forces, there's only two forces, but the sum of the forces goes to zero for equilibrium. That's called equilibrium. Okay. Okay. Okay, so there's one up force and one down force. So I could subtract those and say they zero out, or I could say they're equal in magnitude to each other. So this rho water, gravity, displaced volume. Well, okay, I'll go ahead and subtract them. Okay, minus massive ice gravity goes to 0 newtons. That's true. Okay. 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 Now notice, guys, did I ever anywhere on the paper tell you how large an iceberg this is? Like how many kilograms? No, I never did. Well, that's what this would seem to indicate, the mass of the ice. But wait a minute. What if I have a little tiny iceberg right here, and I have a larger iceberg? Is the percentage submerged going to be the same for both of these? Yeah. Okay, so what I'm trying to hint at you guys is that I think we can replace the mass of the ice somehow in terms of its density, and I think things are going to work out down the line, right? Okay. So here, need some more paper for this though. Okay. So, guys, what is the relationship for? Maybe I'll put this in here. For mass of something and density, how are those related?
Mass per volume density.
Yeah. Density is mass per volume. That's true, right? And if I do mass of the entire iceberg or volume of the entire iceberg, not just the submerged part, but the entire iceberg, that would represent the density of the ice, wouldn't it? Okay. Ooh, so how can you rearrange this to get mass?
It's Anton.
Yeah, density of the ice times volume of the entire ice. Okay. So this right here, I'm going to substitute for the mass of the ice. So it's density of the ice times the volume of the ice. Right? Okay. Right. And then I can continue on down my algebra adventure. So let's go density, water, gravity, volume displaced. Okay. Minus density, ice, volume of the entire iceberg, gravity goes to 0. Okay. All right. All right. Again, add this term over density, water, gravity, volume displaced equals density, ice, volume, ice, gravity. Yeah. Right. Oh, guys, what variable is going to cancel out?
Gravity.
Yeah, gravity field. Which means this. If I take this whole system up to Mars and reset it up on Mars, would the same percentage of this be submerged on Mars? Yeah, sure would be. Sure would be. Yeah. Right. Right. Now, what question is, what percentage is submerged? Which is not a single variable here, but it's a ratio of variables. It's the displaced volume compared to the entire volume. I've got a picture to match this up. Percent submerged is this hashed in volume compared to the entire volume, isn't it? Is that the same thing? Okay. Okay, so really what I want to set up is volume displaced compared to volume ice. I'll say equals. And well, there's two other variables on the board. Can you guys finish off the algebra? You get that? Do you guys come up with that right there? Okay. And those are numbers they got printed out. Actually, that's the only two numbers they gave you for this question. So the percent submerged, which it happens to be this ratio, is right. Now looking at my paper. My paper says 910 compared to 1025 kilogram per cubic meter, kilogram per cubic meter. Your numbers are going to be a little bit different than mine, right? Okay. But I'll feed that in the calculator, see what it says. So I'll say approximately equals 0.8878, or I could call that about 89%. Right, you guys getting the answer on your paper too? Right. All right, so again, that was a process like an adventure I wanted to take you guys through. Right, but the end result is pretty straightforward because you could just plug in the values. Right. Okay, so here's the poster version that I realized I didn't actually print out and put on my wall, I don't think, but it's the same thing. Okay. All right. All right. Now let's do some tough ones, some tough questions. All right, so find a new paper, my line here. Oh, whoops, did I? Okay. Um, let's do number 84. Number 84. Okay. An antique yellow statuette of a bird is suspended from a spring scale. The scale reads so many newtons. My paper says 15.8 newtons. Yours says probably something else. When the statuette is suspended in air. Okay. Hey guys, if you're just hanging it in air, is there a tiny, tiny, tiny buoyant force from the air? Yeah, but it's probably negligible, right? Okay. So we'll say if you were hanging it in a vacuum, it probably wouldn't be very significantly different from that anyway. And the statue reads a different okay, so a different force in the scale when it's submerged in water. The scale reading decreases, doesn't it? Now, there's actually enough information there that you can determine the material that that's made out of. But we'll probably have to be a little bit creative with this. And here, let's try this out. Okay, so I got this. It's a statuette of a bird. Okay, so we'll draw a little bird here, okay. And we're gonna hang this in the air. Okay, and the scale reads. Okay, my scale says 15.80 newtons right there. As it's hanging in the air. Okay. Then we're gonna submerge this in water. And the scale rating goes down. Okay, and my paper says 14.98 newtons. Okay. You guys got yours? Okay. All right. Now let's do a free body diagram for each one of these. Okay. Notice I never told you the volume of the statue or whatever. Okay. Maybe we'll get that along the way. Okay. So I think there's going to be an mg down and a string tension up. That's the first picture. Okay, and okay, well they would both be 15.8 newtons. Okay, so we know that. Okay. Over here, I think the statue weighs the same. Like Earth is pulling on it the same. Right, that doesn't actually change. 8 newtons. But now the tension is a little smaller. This is F sub T, which is now the scale rating, of course, right? But what other force is acting on it now? Buoyant force. So I'll call it F sub B. Okay. Now I think you guys can figure out the value, or how would you figure out the buoyant force?
Okay.
Yeah, you guys subtract these two because the forces have to sum to 0. So I'll just go do that here. So I'll say it's 15.8 newtons minus 14.98 newtons, or 15.8 minus 14.98. Yeah. So mine is going to be 0.82 newtons of buoyant force. And that's F sub B, buoyant force. All right, do you guys figure out your buoyant force? You guys got that?
Like, minus 14.
Yeah, it's gotta be the difference. Yeah. Because this thing actually weighs 15.8 newtons. The scale is only pulling up with 40.8 newtons, that's the tension of the string. So the difference must be the buoyant force is supporting. Yeah, so this number minus this number, like that. Yeah, you guys got that? Okay. Now that we got the buoyant force, let's play around with that a bit. So I'll say buoyant force. Right. Guys, what's a formula you guys know for buoyant force?
Yeah.
Density, water, gravity, volume displaced.
Yeah.
Do that. Let's see where this goes. Can you guys plug in a number for buoyant force? And for me, it would be 0.82 newtons. So I'll go ahead and plug that in there. 0.82, that's newtons. Okay. If we're submerging this in water, do you guys know the density of water?
Yeah. 1,000.
Yeah, 1,000 kilogram per cubic meter. As long as we stick to base SI units, I think we'll be safe. What do you guys feel like using for gravity field? Her 10? Let's go 10. Your second period. Okay. Now, when I put this together on Excel, I don't remember if I used 10 or 9.8, but that's such a tiny difference that probably wouldn't throw out the multiple choice anyway. Okay. Oh, I think we can solve for the volume of the statue. And it would be the full volume of the statue, wouldn't it? Because the statue is completely submerged. So this V represents the volume of the statue. Can you guys find the volume of the statue? All right, so I'll find mine. All I have to do is take the buoyant force and divide by the density of water and gravity field. So, which would be it's about 10,000. Okay, well, okay, so the long version is like this. That'd be cubic meters. Okay. If you like scientific notation, you could write it that way. Yeah, 10 to the negative 5 cubic meters on my paper anyway. You guys getting a tiny volume? Maybe that makes sense because I know 1 cubic meter is really, really big. That's like 1 meter stick by 1 meter stick by 1 meter stick. Because if you had 1 meter by 1 meter, 1 meter, that's a huge box. Okay. If we're talking about like a little like statuette you could put on the shelf. Yeah, it's gonna be a tiny decimal version of that, would it be? Okay. Oh. Oh, good. What's our ultimate goal? What are we trying to find? Density of the statue. Maybe it's made of some material. Okay. And you know what? We just found volume, which could be really, really helpful. Because density is what per what again? Mass per volume. We have the volume. Hey, do you guys see a way we could possibly get the mass of the statue? What do you know that's maybe a similar concept that do you know the weight? Yeah, I know the weight. I think that's the first number I gave you. Right? Good. So if you know weight, you can get the mass. So weight is just mg. And I know the weight. So my statute is this many newtons. We're solving for mass. And okay, we were using 10 meters per second squared for gravity. I wonder if gravity field actually cancels out on this one. I don't know. Yeah, we'll stick to the same value of gravity. Okay. So the mass must be this many kilograms. Okay. Okay. So here I got the volume of the statue. Here, I got the mass of the statue. Aha! All right, you guys ready to go in for the finish? Okay. Because density is mass per unit volume. Mass per unit volume. Okay. So I got this many kilograms mass over this many cubic meters volume. Right. If I take that ratio, it will tell me the density of the material that the statue is made out of. And if I assume it's some solid material, like it's solid, fill in the blank metal, then I could just look up in the textbook and figure out what that material is. Okay. So data point. Okay. I'm getting this many kilogram per cubic meter, right? Now that's a lot of digits of precision. I probably don't know all that precision, but we could say 19,000 and something. Okay, so is that an answer choice? Here's this is my paper I'm working on. Yeah. Oh. Okay, here. Ice Cascade is gold. Yeah, gold. That's what's like. Yeah. All right. So do you guys figure out what your statue is made out of? All right. All right. So a lot of little steps. Right. But if you know the formulas, you can navigate those. Okay. All right.
Sign.
Let's do one right beneath it. I think this one's all right. Number 90. Sorry. 87. What's the apparent weight of a rock submerged in water? The rock actually weighs this value, and the in air, and it has this particular volume. So let's try that. So 87. Now, I like to draw this out. Let's say you got a beaker of water, and you got a scale down at the bottom, and I've got a rock sitting on that scale. Got a rock right here. Okay. And the rock actually weighs, now my paper says 51 newtons. So I'll do a down force. I'll say mg of the rock is 51 newtons. Okay. But there's two upward forces on that rock. Okay. There's the scale pushing up. I'll call it F scale, which is actually a normal force. I guess I could have called it normal force. Okay. There's also a buoyant force, F sub B. Right? Is that true? Okay. So is the scale reading going to be read more than or less than 51 newtons? Yeah, it's got to be less. Okay. Right, so if only I know what that buoyant force is, then I can calculate the difference, and that would be the answer. So I know buoyant force is rho GV. Okay, so let's all go 1,000 kilogram per cubic meter.
I'll go back.
Let's go 10 meter per second squared. And I did give you the volume of the rock. Mine says 2.1 times 10 to the -3 as cubic meters. Like that. Okay. We put that all together. Oh, guys, 10 to the -3 times 10 to the 3. Well, that's a wash. And times this gravity field. I think this has to be 21 newtons of buoyant force. That be the case? Okay. So how I can put that number in? 21 newtons. Okay. Yeah, looking at my answer choices, I may have chosen gravity as 9.8 meters per second squared. So the answer might be off a tiny bit, but there should be an answer choice that's very close. Okay. Now, this scale rating. Okay. Well, these three forces have to sum to zero. That's really the guiding principle from here on out. Sum of forces goes to zero, equilibrium. Okay. Therefore, the scale rating must be the weight minus the buoyant force. 51 newtons, 21 newtons. I'm looking at the difference is 30 newtons, and that's what the scale is actually reading. Okay. Guys right there? Okay. Well, I'd like to fit in another one, but I think we're a little short on time. So let's do this. Guys, double check, make sure your name's on your paper. Is your name on your paper? Just turn in what we did in class. If you think you missed something, you can turn it tomorrow, but you guys probably have done what we did in class. Turn that in. I'll check that off. Make sure you guys are on the right track there. I'll get that back to you guys tomorrow. All right, and then we'll solve puzzles tomorrow and get ready for the quiz.